Hello my friends, and welcome back to Sky Creative Channel. Today we're taking you on an extraordinary journey through some of the most impressive manufacturing processes happening right now in major corporations around the globe. Let's get started.
Let me tell you about a company that's been quietly revolutionizing heavy industry for decades. Simpelkamp Gießerei, based in Germany, isn't your typical foundry. They're the craftsmen behind some of the largest, most complex metal components you'll ever see, the kind that make modern infrastructure possible. Picture this. You're standing next to a piece of steel that weighs over 200 tons. That's heavier than a fully loaded Boeing 747. Yet this massive chunk of metal started as nothing more than raw materials and the vision of skilled engineers. This is the world of XXXXL, heavy-duty forging, where size meets precision in the most spectacular way. Here's something most people don't realize. The steel used in these massive forgings often contains elements that would have been considered exotic just a century ago. Chromium for corrosion resistance, nickel for toughness, molybdenum for high temperature strength. These elements are added in precisely calculated amounts, sometimes just a few tenths of a percent, but their impact on the final product is enormous. The steel chemistry is so critical that Simpelkamp maintains their own metallurgical laboratory, where every batch is analyzed using spectroscopic equipment that can detect impurities down to parts per million. NTHE first step involves heating these massive ingots in furnaces that reach temperatures of over 200-300 degrees Fahrenheit. That's hot enough to melt copper. These aren't ordinary furnaces either. They're computer-controlled behemoths that ensure every inch of that steel reaches the perfect temperature uniformly. The heating process alone can take 12 to 24 hours, depending on the size of the piece. NNBUT. Here's where it gets really interesting from an engineering perspective. The heating isn't just about reaching the right temperature, it's about achieving what metallurgists call soaking. Imagine trying to heat a turkey that weighs 50 tons instead of 20 pounds. The outside would be scorched long before the inside even got warm. That's why these furnaces use a carefully orchestrated heating profile that gradually raises the temperature over many hours, allowing heat to penetrate to the very core of the steel. NTHE atmosphere inside these furnaces is just as important as the temperature. They're filled with a protective gas mixture that prevents oxidation, because even a thin layer of scale on a 200-ton forging represents tons of wasted material. Some of the most advanced furnaces use what's called a walking beam system, where the massive ingots are slowly moved through different temperature zones, much like a conveyor oven, but one that could accommodate a small building. Now comes the truly spectacular part. Watch as this glowing mass of steel, weighing hundreds of tons, gets positioned under a hydraulic press that exerts forces of up to 16,000 tons. To put that in perspective, that's like having the weight of 8,000 automobiles pressing down on a single point. What's remarkable is the precision engineering required to build such machines. The press frames themselves are massive steel structures that must be rigid enough to handle these incredible forces without deflecting. They're often built in sections and assembled on site because they're simply too large to transport in one piece. NNBUT. Here's where the real magic happens, what metallurgists call grain refinement. When steel is cast, it forms large crystal structures that can make it brittle. The forging process breaks up these large grains and creates a fine, uniform structure that's both stronger and tougher. What strikes me most about Simpelkamp's operation is how they maintain tolerances measured in millimeters on components that are meters in diameter. They're using laser measurement systems, computer-controlled machinery, and metallurgical expertise that represents over a century of accumulated knowledge. NTHE cooling process is equally critical. These massive components can't just be left to cool naturally. That would create internal stresses that could cause failures years down the line. Instead, they're placed in controlled cooling chambers where the temperature drops at precisely calculated rates over several days. Some of the most critical forgings undergo what's called stress relief annealing, a process where the entire component is reheated to about 200 degrees Fahrenheit and then cooled very slowly over several days. This process eliminates internal stresses and stabilizes the metallurgical structure. The furnaces used for this process are essentially giant ovens that can accommodate components the size of a small house, with temperature control accurate to within a few degrees across the entire volume. The precision measurement of these massive components requires technology that pushes the boundaries of what's possible. Coordinate measuring machines, CMMs, used for these components can be as large as a warehouse, with measuring arms that extend over 30 feet. These machines use laser interferometry to achieve accuracy levels that are simply astounding. We're talking about being able to detect variations smaller than the wavelength of light on components that weigh hundreds of tons. One of the most impressive aspects is the surface finish requirements. Even though these components are massive, their critical surfaces must be machined to mirror-like finishes. The cutting tools used are often custom-made, single-use items that cost thousands of dollars each, but are necessary to achieve the required surface quality on these exotic steel alloys. What's fascinating about modern heavy forging is how digital technology has enhanced rather than replaced traditional skills. SimpleCamp uses finite element analysis, FEA, software that can simulate the entire forging process before the first hammer blow is struck. These computer models can predict stress distributions, material flow patterns, and even potential defect locations with remarkable accuracy. NBUT. Here's the interesting part. The computer models are only as good as the expertise of the people who create them. The boundary conditions, material properties, and process parameters that go into these models all depend on knowledge accumulated through decades of hands-on experience. It's a perfect marriage of cutting-edge technology and time-honored craftsmanship. One particularly impressive application is the use of real-time thermal imaging during the forging process. High-resolution infrared cameras monitor the temperature distribution across the entire forging, allowing operators to adjust the process in real time to ensure optimal results. This technology, originally developed for military applications, has found a perfect home in the world of precision forging. Every single component that leaves this facility undergoes rigorous testing that would make a NASA engineer proud. We're talking ultrasonic testing to detect internal flaws, magnetic particle inspection to find surface cracks, and chemical analysis to verify the exact composition of the steel. NBUT, perhaps most impressively, they create test pieces alongside each major forging. These samples undergo destructive testing. They're literally broken apart to ensure the main component will perform flawlessly for decades to come. It's this attention to detail that allows these components to operate reliably in power plants, ships, and industrial facilities around the world. NNTHE quality control methods used at SimpleCamp represent the pinnacle of materials testing technology. Ultrasonic testing, for instance, uses sound waves with frequencies far above human hearing, typically 2 to 10 megahertz, to detect internal flaws in the steel. The equipment can identify voids, inclusions, or cracks as small as a few millimeters in components that are several meters thick. It's like giving the steel an incredibly detailed X-ray, but using sound instead of radiation. One of the most sophisticated techniques they employ is phased array ultrasonics, where multiple ultrasonic beams are electronically steered through the material to create detailed 3D images of the internal structure. This technology, originally developed for medical imaging, has been adapted to peer inside massive steel forgings with remarkable clarity. And magnetic particle inspection is equally fascinating from a physics standpoint. The component is magnetized using powerful electromagnets, and then fine iron particles are applied to the surface. Any surface cracks disrupt the magnetic field, causing the particles to cluster and reveal even hairline defects that would be invisible to the naked eye. This technique can detect cracks that are only a few thousandths of an inch deep. Remarkable sensitivity for such massive components. NTHE finished products from SimpleCamp find their way into everything from wind turbine generators to the massive presses that shape automobile bodies. Every time you flip a light switch or drive your car, there's a good chance you're depending on components that were forged in facilities just like this one. Now, let's shift gears and talk about something that literally keeps the world turning: massive roller bearings. MTK Bearings has mastered the art of creating these precision components that can be over 6 feet in diameter, yet maintain tolerances tighter than a human hair. These aren't the bearings you might find in your bicycle wheel. We're looking at components that weigh several tons each and are destined for wind turbines, mining equipment, and industrial machinery where failure simply isn't an option. NTHE manufacturing process begins with premium bearing steel that's been specially treated to achieve the perfect hardness. Hard enough to resist wear, but not so hard that it becomes brittle. The outer and inner races are machined using computer-controlled lathes that can hold tolerances of just a few microns across surfaces that span several feet. Not remarkable is watching the roller installation process. Each bearing contains dozens of massive steel rollers, each one individually inspected and measured. The assembly happens in clean rooms that rival semiconductor facilities because even a speck of dust could cause premature failure in these critical components. NTHE final testing is where MTK really shines. Each bearing is subjected to loads and speeds that simulate decades of real-world operation, compressed into just a few hours. Only after passing these grueling tests do these bearings earn their place in the massive machinery that powers our modern world. Let's take a journey into the world of railway wheel manufacturing with Lucchini RS, a company that's been perfecting the art of railway wheels for over a century. When you think about it, railway wheels are one of those components we completely take for granted, yet they're marvels of engineering that must withstand incredible stresses while maintaining perfect roundness mile after mile. Lucchini represents the evolution of craftsmanship that began in the steam age. Their wheels don't just support trains, they're the critical interface between thousands of tons of rolling stock and the steel rails that guide them. Every wheel must be absolutely perfect because a failure at 200 miles per hour isn't just inconvenient. It's catastrophic, and an THE process begins with steel that's been specifically formulated for railway applications. This isn't ordinary steel. It's an alloy that must resist wear from constant contact with rails, withstand the thermal stresses of heavy braking, and maintain its structural integrity through millions of rotation cycles. And watch as these raw steel blanks are heated to precisely 100 degrees Fahrenheit in computer-controlled furnaces. The temperature is critical. Too hot and the steel grain structure becomes coarse, too cool, and the metal won't flow properly during forming. The heating process takes several hours, with the temperature being monitored by infrared sensors that can detect variations of just a few degrees. Now comes the spectacular transformation. The glowing steel blank is positioned in a massive hydraulic press, and I mean massive. We're talking about 8,000 tons of force being applied in carefully controlled stages. But here's what's fascinating. This isn't just about applying pressure. The experienced operators are using techniques that have been refined over generations of wheelwrights. NTHE initial pressing creates the basic wheel shape, but achieving the precise profile requires multiple forming operations. Each step is calculated to ensure the steel flows exactly where it needs to go. The rim of the wheel must be perfectly round to within a few thousandths of an inch, while the hub must have the exact dimensions to fit the axle with no play whatsoever. After forging comes machining, and this is where modern technology really shines. These wheels are mounted on lathes that are as large as some machine shops, with cutting tools that can maintain tolerances measured in fractions of millimeters across wheels that are 3 feet in diameter. NTHE. Most critical surface is the tread, the part that actually contacts the rail. This surface is machined to a mirror finish, because any imperfection will create vibrations that passengers will feel, and that will cause premature wear of both wheel and rail. The profile is precisely calculated to ensure proper contact with the rail crown, optimizing both performance and longevity. And NBUT, here's where Lucchini's expertise really shows. After machining, each wheel undergoes a heat treatment process that would impress metallurgists from any era. The wheels are heated again, this time to very specific temperatures that vary across different parts of the wheel. NTHE rim needs to be harder than the center to resist wear, but the center needs to be tougher to absorb shock loads. This differential heat treatment creates a wheel that's optimized for its specific application: passenger service, freight hauling, or high-speed rail operations. Every single wheel undergoes testing that's absolutely mind-boggling in its thoroughness. We're talking ultrasonic testing to detect any internal flaws, magnetic particle inspection to find surface cracks invisible to the naked eye, and dimensional checks using coordinate measuring machines accurate to within microns. NBUT, the most impressive test, is the rotational testing. Each wheel is spun at speeds far exceeding what it will ever see in service, while loaded with forces that simulate the worst possible operating conditions. Only wheels that pass this grueling test earn the right to carry passengers and freight on railways around the world. NTHE finished wheels from Lucchini RS find their way onto everything from subway cars in New York to high-speed trains in Europe. Every smooth ride you've ever taken on a train was made possible by the precision and craftsmanship we've just witnessed. Our final stop takes us to Iraq, where Hanwha E&C has established one of the most sophisticated concrete manufacturing operations in the Middle East. They're producing pre-stressed, high-strength concrete piles, or PHC piles, that form the foundations of modern construction projects. This isn't your typical concrete operation. This is precision manufacturing applied to one of construction's most critical components. Let's start with the raw materials preparation. The steel reinforcement begins as high-strength steel bars and wire, specially selected for their tensile strength and durability. These materials undergo rigorous testing before they're even allowed into the facility. We're talking chemical analysis, strength testing, and dimensional verification. NTHE steel bar cutting operation uses precision saws that can cut through 3-inch diameter steel bars like butter, maintaining cut angles accurate to within a degree. Each cut length is verified because the pile's structural integrity depends on these reinforcing bars being exactly the right length. NNTHE steel bar heading process is where engineering meets artistry. High-pressure dies form the ends of these steel bars into precisely shaped heads that will later connect with tensioning equipment. The heading machines apply tremendous force, over 500 tons, in a fraction of a second, cold forming the steel into complex shapes while maintaining the bar's metallurgical properties. Now watch this fascinating process, coiling the wire around the steel bar. This isn't random wrapping. Every coil is positioned with mathematical precision. The spacing, tension, and pitch of these coils has been calculated to provide exactly the right amount of lateral reinforcement. Automated equipment ensures that each coil is identical, because consistency is what separates professional-grade manufacturing from craft production. NNTHE transfer to case and shoe assembly represents manufacturing choreography at its finest. Each pile moves through the facility on precision tracks, stopping at exact positions where automated equipment performs specific operations. The case assembly process involves positioning hollow steel forms that will shape the concrete. These aren't simple tubes, but precisely engineered forms with complex geometries. The concrete input stage is where chemistry meets engineering. This isn't ordinary concrete. We're talking high-strength mixed designs with compressive strengths exceeding 8,000 psi. That's stronger than most natural stone. Computer-controlled batching ensures that every cubic yard of concrete has exactly the right proportions of cement, aggregates, water, and chemical admixtures. NTHE concrete flows into the forms under carefully controlled conditions. Vibration equipment eliminates air pockets while ensuring the concrete completely surrounds the steel reinforcement. Too much vibration causes segregation. Too little leaves voids that compromise strength. Here's where the pre-stressed part of PHC becomes critical. Hydraulic jacks apply tremendous tension to the steel reinforcement. We're talking about forces that would lift a locomotive. This pre-stressing is what gives these piles their incredible strength and resistance to cracking under load. NTHE bolt tightening operation requires precision timing and force control. Each tensioning operation is monitored by computer systems that ensure the exact specified force is applied and maintained throughout the curing process. NNTHE rotary molding process is truly mesmerizing to watch. The entire pile assembly rotates while the concrete is still plastic, using centrifugal force to achieve uniform density and eliminate any remaining air bubbles. This process, borrowed from pipe manufacturing, ensures that these piles have consistent strength properties throughout their entire cross-section. NNTHE 12-hour steam curing cycle represents a perfect balance of time, temperature, and humidity. Steam chambers maintain temperatures around 140 degrees Fahrenheit while keeping humidity at 100%. This accelerated curing allows the concrete to achieve in hours what would normally take weeks of natural curing. NNTHE demolding and final processing stages reveal the finished product, perfectly straight, uniformly colored concrete piles with strength properties that would amaze the concrete pioneers of the early 1900s. Each pile undergoes final inspection, including strength testing of companion samples cast alongside the production piles. These PHC piles will become the invisible foundations of buildings, bridges, and infrastructure projects throughout the Middle East. Every time someone enters a modern building in the region, they're depending on the precision manufacturing we've just witnessed.